Starting a swing involves changes in center of mass and mechanical energy.
From this clip, you can see the center of mass in the x direction lies at the center of the swing at the black dot. This point is directly below the pivot point of the swing.
When standing on one side, the center of mass in the x direction does not change. It stays at the black dot. The point where the center of mass used to be, however, is lifted higher.
This is what you got to know. Love you though it didn't show.
As the person on the swing shifts his weight, the swing will move to a position of lowest potential energy. This point will always be directly under the pivot at the black dot.
Da da da. Da da da.
Now when two people are placed onto the swing is put into motion by changing the center of mass in the x direction and gaining potential energy, which is then changed into kinetic energy. As one person leans back, the other person will lean forward. As shown before, the center of mass will stay under the pivot point, but because the radius is fixed and the swing is rigid, one end will be raised up into the air. At this point, the two people will change directions. This movement changes the center of mass to the other side that is already raised into the air. This action creates potential energy.
Because the center of mass is not at a stable position directly under the pivot, the potential energy is converted into kinetic energy and the swing begins to start moving. When the swing reaches the amplitude on the opposite side, the two people again shift directions and potential energy is gained. This series of movements will build up more and more potential energy that is changed into kinetic energy, and the swing will get higher and higher.
After all is said and done, it was right for you to run.
I like girls that wear Abercrombie and Fitch. I take her if I had one wish.
We can find the velocity at the bottom of the swing by using conservation of mechanical energy.
We first find the center of mass of the swing simply by placing the swing on a bar as shown and finding the balance point. Using a radar gun, we drop the swing from a point with an angle of 38 degrees and measure the velocity. After 3 trials, we obtained an experimental velocity of 3.11 meters per second.
We also took a reading of the velocity when people are standing on the swing. Surprisingly, after 3 trials, the average velocity was the same, 3.11 meters per second. We believe this happened because the center of mass did not change significantly in either the x or y direction, enough to change the potential energy at the amplitude and therefore kinetic energy through the bottom.
To find the theoretical velocity through the bottom, we must first find the height that the center of mass raises to.
Then, using conservation of mechanical energy, we can find the velocity of the center of mass through the bottom.
Using the velocity of the center of mass, we can find the angular velocity of the swing. Then we can convert that angular velocity back into a linear velocity and use the length of the swing, 1.9 meters, as the radius. This will give us the theoretical velocity at the end of the swing.
The walls are closing in, but that's okay, cause I've been waiting all week to feel this way. And it feels so good, so good. I'm on top of the world, the coolest kid in the neighborhood. So let me be.
To find the moment of inertia of this swing, we can use the formula for the period of a physical pendulum, where t is the period, I is the moment of inertia, and d is the distance to the center of mass. We start by timing the period of the swing. After 3 trials, the average period was 2.65 seconds. We obtain a value of 41.20 kilograms meters squared. We can find the theoretical moment of inertia of the swing by treating the object as 2 separate parts, and then adding the separate moments of inertia together. The 2 hanging supports of mass 8.18 kilograms and length 1.9 meters can be treated as uniform rods with the axis of rotation through the end, with moment of inertia 1/3 m1 L squared. The bottom platform of mass 10 kilograms can be treated as a moment of inertia of a point with length L 1.9 meters from the axis of rotation. The theoretical moment of inertia of the swing is calculated to be 45.95 kilograms meters squared.